All right, let's get the show started. Hello, everyone. Hope you're well. It's another nice day out, but of course, it's even better being here doing math, as we can all agree. Let's actually jump into it. We've been waiting, so let's move on. The next topic I actually want to cover is 2.9. So there are things that I want to talk about in 2.8. I will actually mention a little bit of that after covering this section. But yes, as some of you are aware, you have a bunch of homeworks being due relatively soon, as well as your first test is actually not that far away. Your first test is like a week from tomorrow or something like that, if I do recall. 2.8, there's a lot of theory in 2.8 and a lot of things that I think are important to touch on, important to talk about, but I kind of want to get through the more computational type things that you're going to need for your exam and you'll need for getting through your homework. And I'll probably talk about, I'll talk about that theoretical stuff that applies to 2.8, and I would probably do the theoretical stuff I want to talk about when we hit chapter 4 around the same time, actually. So we're just going to postpone that. I will mention some things because we're going to be doing things that might seem strange when you don't have the theoretical background. Yeah, it's actually pretty quiet around here. Just got me out of my train of thought. Okay, so we're going to skip over 2.8. We're going to go to 2.9, but we'll come back to talk about some of the things in 2.8, which are more conceptual when after the first exam. Last time we covered exact equations. Hopefully you guys remember what that is. So an exact equation was just one that had this form. And we saw how to solve those. The process was just using integration, which is relatively simple in the sense that we would know what to do. The integrals themselves might be complicated, but whatever. We also saw a situation that there were times when we had an equation that was not exact, but we could make it exact by actually multiplying through by an integrating factor. In order to find the correct integrating factor, it amounts to solving a PDE, which is in general very difficult to solve, but we have a couple of situations that we understand very well. And so those are the situations that I expect you to know how to solve. So those are represented in this box here. And so if we're given an equation, there are times when it's not any of the forms that we saw before. It wasn't separable, it wasn't linear, it wasn't homogeneous, it wasn't exact, but we can multiply it through by an integrating factor to make it exact. And we looked at that. The next thing I'm going to want to cover is from section 2.9, where we're going to look at some miscellaneous problems and techniques that you would need to know. The first one here, called reduction of order, this is something that we're going to be doing in a more general setting later on, and it's in 3.4, I want to say. And I only know the section number because I was looking it up when writing the notes. Like in general, I don't remember the section number. Someone mentioned 3.8 earlier. And I'm like, I don't know what that is. But yeah, so it is something that we're going to cover. But basically what I want to talk about, these are situations in which sometimes they can be second order. Notice that there's a second derivative here, but we can look at them from the perspective of first order. And sometimes there are first order ODEs with very specific forms, and we have strategies for solving them. Another form that we won't talk about is called the Riccati form, a Riccati equation. And that's also in this section 2.9. So what I want to do here is we just want to talk about some other types of ODEs that we know how to solve very well and that we want you to be able to solve. So that's what this section is going to be about. So let's actually just jump into it. So today's class is going to be a lot, and tomorrow's class as well, is going to be a lot about learning new techniques to solve new types of differential equations, just going through like a drill form. Here's a type of ODE, here's how you solve it. Here's a type of ODE, here's how you solve it. And we're segueing into second order ODEs right now. There are times when we can have a second order ODE and we can actually think about it as a first order ODE and actually solve it using methods that we've seen before prior to this class. So here's one case. This is a case in which there's a method called a reduction of order that can work. So this is when you have a second order ODE that is of the form, well, the form can look like whatever. However, it's in a situation where the dependent variable is missing. So remember, the independent variable here is t, that's our input. The dependent variable here is y, and then we have the derivatives of y, the first derivative and the second derivative. Once the second derivative is the highest derivative visually present, we call it a second order ODE. However, if you are looking at such an equation and there is no y term, as you can see, for example, this guy here, there's no y in that equation. So it is a second order ODE, but the dependent variable is visually missing. It turns out that for these guys, you can actually use a method called reduction of order. And as the name suggests, we are going to reduce the order. So it's a second order ODE, but we are going to reduce the order and think of it as a first order. Now, this just comes from the fact that we can see that there's a pattern here. Knowing that the second derivative is just the derivative of the first derivative, this means if I think of the first derivative as just some dependent variable, as some function, then the second derivative is just the derivative of that function. So if I replace my y prime with a variable, then the y double prime is just replaced with the prime of that variable. So reduction of order amounts to a substitution strategy. Set v equals y prime, which means that your v prime would be y double prime. You're going to plug this into the ODE. You're going to be able to rewrite it as a first order ODE, and then you're going to use previously learned techniques to solve the ODE. When you're done, of course, you're going to get a solution that involves the variable v. What you're going to do is you're going to back substitute for v. So you're going to plug in y prime for v at the end, and then solve for y via integration. So this is the basic strategy. So there are times when you see like a second order ODE, but the dependent variable is missing. And so what you can do is just replace the derivative with a variable. The second derivative is going to be the derivative of that variable, and now you're in a first order case. So let's actually do that here. So this is the first example. We're going to go through here. So why am I right? So here, the first thing I'm going to do is note the dependent variable. Y is missing. However, I see the first derivative and the second derivative accounted for. Whenever you do that, you can do a substitution. Set v equals y prime. This means that your v prime is going to be your y double prime. This means you can go back to the original and you can just replace it. So instead of y prime, you now have y double prime, you now have v prime. And instead of y, you now have v. And what you will notice, this is a first order ODE. In fact, now this is someone classify this for me. What kind of ODE is this? Right, first order linear. Hopefully you see that it's linear. Okay, so now you know that it's first order linear. How do we solve it? So you recognize it's linear. What's the method? Mu, how do you find mu? Move the 1 to the left. Then divide by t squared, right? You have to remember that you must put it in standard form first. Then your mu is? Right, e to the integral of the p, which is the coefficient of the v, right? So that's going to be dt. This is e to the 2 ln of t. That's just actually going to be t squared, which means it was already in the right form. So if you multiply through, this is just going to be t squared times v all prime, which you'll notice that the original was actually in that form already, but whatever, didn't waste too much time here, equals 1. So this means that t squared v is going to be equal to t plus some arbitrary constant, which means that your v is going to be equal to divide by t squared 1 over t plus ct to the minus 2. So that is actually the solution. Here's an equation that relates my new dependent variable with the independent variable. And so now what I do is I do the back substitution. So here's what I'm talking about when I say back substitution. I'm going to introduce the y back. So the v was y prime. So now I have y prime is equal to this. And so now, didn't the 1 divided by t squared, where was that? You mean here? Yeah, but we found that the mu was t squared, and then we multiplied this equation by t squared. Yeah. It turns out the original equation, the left side was already in the form of the product rule. So when we found the integrating factor and we multiplied through by it, we actually got back the original. It turns out that the left side was already in product rule form. So here, we can find the y by just integrating, right? So I'm going to integrate both sides here. And so my y is going to be ln of t minus, now you could put a plus. There was a situation in web work where it had it insisted that the answer was a minus c instead of possibly a plus c. Normally I tell you don't worry about the signs on the constant. So you could put a plus or minus here, it won't matter. Okay, to put plus. Because when you actually start, if you want to solve for the arbitrary constant, when you actually start plugging in values, you'll get the value of c with the right sign that you need anyway. So the negative is not necessary. Anyway, so you integrate both sides, you get a second constant here. So note we have, note, and this is something we'll talk about a little bit. We have 2 arbitrary constants. And this is going to be a theme. In general, when we're looking at linear ODEs, the number of arbitrary constants is going to be the same as the number of the order of the equation. So we have a second order, you should expect 2 arbitrary constants. You have a third order, you should expect 3 arbitrary constants, and so on and so forth. And a part of this is because to go from like a y triple prime, you'd have to integrate 3 times. You're going to get 3 arbitrary constants. If you're going from a y double prime, you have to integrate 2 times. You're going to have 2 arbitrary constants. Going from a y prime, you have to integrate 1 time. You're only going to have 1 arbitrary constant. So in this case, you can have 2 arbitrary constants, but that is actually going to be your answer. This is the solution to that ODE. And essentially, we found that by thinking of it as a first order, even though it was technically a second order, simply going through that substitution allowed us to think of it as a first order ODE. So that's it. This is one scenario that you can find yourself in. You can have a second order ODE. However, the dependent variable is missing. This allows you to do a substitution like this. That will immediately bring it to a first order. And once you're there, now you just want to identify what form is it, like what we've covered before. Is it separable? Is it linear? Is it homogeneous? Is it an exact equation? Whatever it can end up in a variety of forms, but you should be able to identify the form it's in as a first order and be able to solve it from there. This case, it was linear, so we solved it with the integrating factor method. Ultimately, we ended up with our solution here. Has 2 constants of integration, which makes sense because it was originally a second order ODE. So yeah. that is one scenario you can find yourselves in. This is a scenario that works well with reduction of order. And as long as you have two derivatives appearing and they're one derivative apart, you can actually do a method like this. So for example, if I had a y triple prime and a y double prime in the second part, I could set v equals y double prime. Then my v prime would be the y triple prime, and I've reduced a third order to a first order, right? So whenever you only have two derivatives present and they're one derivative apart, you can actually think of that equation as a first order equation. That's called a reduction of order. Very useful thing. And this is actually this technique, we're going to use it in general to derive some important facts later on. But that's just an introduction to this technique in chapter 2. Here's another case. I left a lot of space here. Here's another scenario in which we know very well how to solve ODEs in this scenario. How many examples did I give? I gave one example. Okay. So this is a very special kind of equation. It is called a Bernoulli equation. The method shown here was actually, the method for solving these that I'm going to present to you was actually the one discovered by Leibniz, the same guy who invented calculus alongside of Newton as we know it today, back in the 1690s. But these are called a Bernoulli equation. Now they have a very special form. It's like they have the left side of a linear, but the right side is different. The right side is specifically, looks like the form q of t times y to the nth power, or y is your dependent variable. Any equation of this form is called a Bernoulli equation, or a Bernoulli first order equation. And there's a very nice way to solve these when none of your previous methods would work. You should note that there are situations here where your previous methods would work. For example, if your y equals 0, this actually becomes a linear first order, because if y to the 0 would be 1, and so this would look exactly like a linear first order. If your n equals 1, then over here is y. You can bring these guys over, combine them, pull out the common factor of y, and divide by it. So it's actually separable if n equals 1. So in the case where n equals 0 or n equals 1, we actually can solve it by previous methods. The interesting thing comes in when we have other values of n. So n here can be any constant. And if we have another value, like what if n is 3? What if n is 17? What if n is pi? How would we solve it? It turns out we have a nice strategy for this one, which is the strategy discovered by Leibniz. Basically, you're also going to do another substitution, but you're going to do this substitution specifically. V equals y to the 1 minus n. And you're going to realize why this is actually useful in the beginning. Well, as we're going through. But I guess I can kind of tell you here. Notice that here, if I start to differentiate this using the chain rule, I'm going to ultimately bring this power down, subtract 1 from the power, multiply by a y prime. If I subtract 1 from the power, I get a y to the minus n. And notice that y to the minus n is what's going to kill the y to the n over here. So you're actually going to see this in action. But basically, if you're in a Bernoulli equation setting, this is now a new type of differential equation that you should know, which is why I put it in a box. You can actually do this strategy. Make the substitution v equals y to the 1 minus n. This is going to turn it into a linear first order. You're going to solve it using previously learned techniques. And once again, you're going to back substitute. So here's a situation. Notice that this guy here, I can think of it as this y prime plus 2ty equals y cubed. So here, notice that this is Bernoulli. With n equals 3. Okay, so this looks like this definition here. My q of t is 1. My p of t is actually 2t. Well, my p of t is what I would get when I divide through by the t squared. Okay, so this is an equation, and I can now identify it as Bernoulli. Once you recognize it's Bernoulli, this is the method that you go by. So what we're going to do is we're going to set v equals y to the 1 minus 3, y to the 1 minus n. Okay, so that is your v is y to the minus 2. Now what you're going to do is you're going to find v prime. You are going to set that, and you can do that just by differentiating this equation. So that's going to be minus 2 y to the minus 3. There's your y to the minus 3. That's going to end up killing this y to the positive 3 times y prime. This means I can solve for y prime. So in this case, my y prime is going to be y cubed over 2 times v prime minus y cubed. And now what we are going to do is going to plug into the original ODE. So my y prime, I'm going to replace with this guy. So I'm going to have t squared times minus y cubed over 2v prime. That replaces the y prime, plus 2ty equals y to the minus 3. Well, y cubed. Okay, and now look what happens when I divide by y cubed. So what you normally do here is you divide by y to the n. Yeah, the y cubed was in the original. The y cubed is here. Right, this was the given equation right here. I just moved the y cubed to the other side. So it's all equal to y cubed. What you're going to do is you're just going to replace the y prime. Everyone else is going to fall in line. This is going to magically turn into a first order equation. No, not right away. So you're going to see what's going to happen. Just replace the y prime. Replace y prime. So when you plug this into the original, you're going to get this. Just replace the y prime. Now look what's going to happen. I'm going to divide both sides by y cubed. So this means I'm going to have minus t squared over 2v prime plus 2t y to the minus 2 equals 1. So this guy here was your y prime. Notice what is this guy here? Y to the minus 2. Well, that is what we said v was in the original situation. So this here is v. And now I can actually rewrite this again. So this is minus t squared over 2v prime plus 2tv equals 1. And look at that. We now have a first order. This is actually linear. I'll just tell you guys. This is actually linear. And it's now a linear equation where t is the independent variable and v is your dependent variable. Now, of course, in this scenario, our v is y to the minus 2. And so now, after I solve this for v, I can replace it with y to the minus 2, then solve it for y. And yes, I completely agree with you, Jason. It is very cool, right? So Leibniz noticed this very cool way of attacking this kind of integral, which is a very important integral. It's what are you lost with? So starting from the beginning, this is a Bernoulli. That's the definition. This is the strategy that we use. Plug in v equals this substitution. You differentiate both sides of that and you plug it in. So we started here. We moved the y to the other, y cubed to the other side. That way I could identify it as a Bernoulli. Now I do the substitution, right? Y equals y to the 1 minus 3. Why do I do that? Well, that's the strategy here. But I do that because of this is going to be easy. This makes the equation nice. And so I solve for my v prime. This allows me to solve for y prime. I plug in the y prime. That leaves me in this scenario. Are you okay up to this point? No. Okay, so your confusion happened before. Does it happen here? Okay. So this scenario, this part here comes from taking the original equation, this guy, and I literally just replace the y. I replace the y prime. The y prime, I just put in this in place of the y prime to get this. That's all that happens. I plugged in the y prime. So I did the substitution. I differentiate both sides of the substitution. That helps me solve for the y prime. Then I go to the original and I plug in that y prime. And so now I have this new equation. Once I'm in that new equation, I start to simplify. I can simplify by dividing both sides by the y to the n, which in this case is y cubed. If I divide through by y cubed, I get this equation. Yes, there will always be the pattern to substitute for the v. Yes, yes. I mean, come on. This is Leibniz thinking about this method. He thought about this is the guy who invented calculus, remember? So he knows what he's doing. This substitution takes care of everything. You will always end up in a scenario like this. You will if you're in this situation, this substitution will always take you to a first order equation where v is the dependent variable and t is the independent variable. Yeah, you'll always notice that v is going to show up. Again, because there's the y here. When you multiply that, remember what we're doing here is we're multiplying both sides by y to the minus n. If you take y and you multiply by y to the minus n, you're going to get y to the 1 minus n. So this part here is always going to happen because there's always going to be a y in this scenario. So when you divide by this guy is always going to end up being the v. And then our substitution allows us to replace the y prime again with a guy that will simplify by this guy. This guy here is always going to end up in this in a numerator position here, so that when I divide both sides, the y's disappear from this first part, and then the y here is going to just become the v. It's always going to work out that way. Yeah. Right. And that's what we call, as Jason put it, very cool. It's very cool. It always works out to a situation like this. Taking this substitution and following it to its logical conclusion always brings you to a first order situation where all the y's are gone. All right. Now at this point, once you're here in this first order situation, I've taught you many techniques for dealing with this. And this is, again, something familiar. It's, again, a first order linear. So what I would do is I would just rewrite it as a first order linear. So I can divide, multiply by 2, and then divide by so I multiply by 2 over t minus 2 over t squared, the whole equation. And that puts it in the situation where I can find my mu. Mu is going to be e to the integral of the minus 4 over t. This is going to be e to the minus 4 ln t. This is pretty much going to be t to the minus 4. And I'm going to go through and I'm going to multiply that. Now, the left side is going to be t to the minus 4. I keep writing e here. Times v, all prime. The right side is going to be, I'm going to multiply this by t to the minus 4. That's 2t to the minus 2. So this becomes minus 2t to the minus 6. Then I integrate both sides. This side is going to become t to the minus 4v. That side is going to be, you add 1 to the power, divide by the new power, plus a constant. Now I multiply both sides by t to the 4th. That allows me to solve for v. And then I replace my v with y to the minus 2 because that's what it is. So what we're doing here is back substitute. And so now my y is just going to be, well, plus or minus the square root of this guy. Where the plus or minus, we can determine which one we need if we're given an initial condition. Initial. Initial condition. And it was a negative 2, so it's actually 1 over this square root. Okay, any other issues here? Yeah, so y to the negative 2 is just 1 over y squared. So I take the reciprocal of both sides and then take the square root, and I get this. Positive 2/5. Should it be positive 2/5? Add 1 to the power is minus 5, divide by the new power. So yes, that is a positive 2/5. Anything else? It's good that you guys are paying attention. I don't know why. It's funny that you guys are paying attention. You should be, but I'll take the haha whenever I can get one. All right, let's see here. And so that's another situation. This is called a Bernoulli differential equation. Very common. These equations are common enough for us to actually give them a name, and they're named after one of those big names in mathematics, Bernoulli. It's really nice. Bernoulli, it's kind of like you're saying Mercedes when it comes to cars. You're in math, you say Bernoulli, you're like, ooh. You know, it's a very long line of prestige behind the name Bernoulli. It's like a whole math family. A bunch of dudes in that family were like really influential math people. So here's another situation. Let's actually maybe move this. Move these guys closer to the other ones. So that was the Bernoulli situation. Here's another situation that, and this is the last situation that I'm going to show you guys for this section. Okay, so this is the case. So we're doing 3 case studies in this section. This is the case where our independent variable is missing. So we have a second order ODE, but if I said the t is the independent variable, the t's are missing. So I can see a y double prime, I see a y prime, I see a y, but there are no t's. Another thing, these guys are also called autonomous ODEs. But I don't think you need to know that phrase. Autonomous ODE. Right. Whenever your independent variable is missing, you call it autonomous. And we actually have a strategy for that as well. Now, this one can get a little hairy. The other 2 are more or less straightforward, the other 2 situations I show you. But this one is a little bit, can get a little bit on the complicated side. So here's the strategy for this one. So your independent variable is missing. So what you're going to do is you're going to do another substitution. It starts out very similar to a previous one. You start with v equals y prime. The idea is the substitution you're going to do. Now, of course, that will allow you to solve for v prime. And you can plug this in. However, you're not going to end up in a nice situation like in Bernoulli where all your y's are going to cancel out. So you're going to have like a v, you're going to have y's all over the place, and then you're going to have an independent variable called t, which there are now too many variables for this scenario. So to prevent there being too many variables, you actually rewrite v prime in another way. You apply the chain rule from Calc 1 to rewrite the v prime. So you don't think of v prime as y double prime specifically. You think of it as dv dt, which you break down into dv dy times dy dt. Now the dy dt is actually just the v prime, so you swap that in, and so you have this. And so now your y double prime can look like this expression, where you have dv dy times v. Now what you will notice about that expression is it's assuming that the y is now the independent variable. So you're now changing both the dependent and independent variable. And so now you can get a first order scenario in which the y is the independent variable and your v is the dependent variable. And then you solve that. And then you do the back substitution, and then you can solve the equation, right? So ultimately, this strategy comes down to the following. You know you're in a situation like this where your independent variable is missing. What you're going to do is you are going to replace the y prime with v. You're going to replace the y double prime with dv dy times v. This is going to give you a first order equation. Solve that equation. In this equation, your y is your independent variable and your v is your dependent variable. Once you solve for the v in terms of y, you're going to replace the v with y prime and then solve for the y. Let's do 2 examples here. Let's move this one out of the way. So this is example 3A. So here's an example. And here's something that, the method is a little bit annoying. However, it is quite powerful. As you'll notice, this equation here is not even a linear equation. It is a nonlinear equation, which those guys are actually harder to solve in general. But this technique can deal with this scenario because notice that there are no t's. So here I'm thinking of my y as a function of t, right? So y is y of t, right? So the independent variable is t originally. But looking at this, the t is missing. Note, t is missing from this equation. Visually, I cannot see it. So this allows me to go into this substitution that I mentioned up here. And that substitution is actually going to, believe it or not, help us out. I'm going to set v equals y prime, and my y double prime is just going to look like dv dy And I'd write this out with the Leibniz notation because I don't want you to get mixed up and thinking that that your t is still your independent variable. With the prime is the notation I use when I'm thinking of t as the independent variable, but here I'm switching to a situation where y is the independent variable. So I'm going to make these two substitutions specifically. Now, if I do that and I go in and I plug in this, what's going to happen? Well, I'm going to have y times y double prime, which is dv dy times v, plus I'm going to have v squared, because my y prime is v, and my y double prime is the guy that's here. So I simply just replace them, I plug them in. Here I can divide through by v if you want. So I have y dv dy plus v equals 0. Now notice that that is a first order equation where I'm thinking of my y as the independent variable. This one is actually separable. So I'm going to separate the variables here. So this is y dv dy, can move minus v over there. Then what I'm going to do is I'm going to divide by v, and I'm going to multiply by dy, and then divide by the y. So I get that. So this is now separable. I can integrate both sides. Remember that if you have ln of something plus a constant, you can write that as ln of a constant times the thing. And of course, this is going to be -1 because I can move this minus thing up to the power by the laws of logarithms. And so I can drop that. My v is now going to be just some constant times y to the -1, where whether the absolute value is going to give me a plus or a negative applied to this, the c is going to take care of it. So I can leave it like that. Now, my v is actually y prime. So I'm going to do the back substitution. And so my y prime is that guy. Now, again, this is going to be separable. This is my dy dt now. I'm back to t being the independent variable. And this is c over y. So I get y dy is equal to c dt. And I separate again. Integrate both sides. I would get y squared over 2 is equal to ct plus another constant. And so I have my y squared is equal to, I can multiply both sides by 2. So it looks like ct plus d. And that's an implicit solution. I can take the square root if I wanted to. And so we have that guy. Okay. So here we have an equation where the independent variable is missing. What I can do is I can set v equals y prime. Y double prime is going to be equal to dv dy plus times v. And that follows by the chain rule. Let me rewrite the double prime here. Okay. By the chain rule, we can get that. And then I plug into the original equation. That is going to be a first order. It might be separable, it might be linear, it can be whatever. But it's going to be something that you know how to deal with because it's a first order. We know about a lot of those situations. And so what we have here, in this case, it was separable. So I separated the variables, solve for the v, back substitute for the v, and then solve for the y. Why is there a v in the y double prime? Oh, I mentioned that in the notes here. So if my v is dy dt, then I can think of dv dt, which is the y double prime, as dv dy times dy dt. And the dy dt is the original v. And so that's where I got the dv dy times v from. It's an application of the chain rule. We did that early on. It's hidden in these substitutions. But I derived the substitution here. No, y prime times y prime is not, it's not y double prime. No, y double prime is the same as y prime prime. If you look at y prime times y prime, that's actually y prime squared, which it's actually not the same thing. Yeah. So this way, how I'm doing it, it's not y prime times y prime, because this is dv dy. That's not even a y prime right there. So I just use the chain rule and we apply that. We apply the chain rule to v prime, and that's what we get when we apply the chain rule. Okay, let's look at, where was the other example? Here's another example. We're going to look at two ways to do this. So I'm going to look at the way that's shown here, and I'm going to show you a way after that, because you're going to realize why we want to look at another way. Take advantage. Okay, let's say this is a new equation. Notice again, again, I'm thinking of my y as a function of t. So t is the independent variable original. So here, what you're going to notice is t is missing. Right. So you notice that your t is missing. Once you notice your t is missing, the previous scenario, that the previous strategy that I gave you can work, which means you're going to immediately start thinking of this strategy here. Step one, make these substitutions. Step two, you're going to get a first order, solve it by any means necessary. Step three, step two is not even an actual step. That's just what you're going to end up with. Step three, you're actually going to solve it. Step four is you're going to actually do the back substitution. So we're going to do that. I noticed that my t is missing. So let's actually do that. So I'm going to set v equals y prime, and I'm going to set my y double prime equals dv dy times v. Plugging this into the original, I'm going to get dv dy times v, that replaces the y prime, plus v squared, that replaces the y prime here, equals 2e to the minus y. And so now this here is going to be dv dy. I can like divide through by v. And there's going to be a v over here if I do that. Put the v over here. In other words, this is going to be a dv dy plus v equals 2e to the minus y v to the minus 1. Okay, now what kind of equation is this? It's not linear. Remember what linear means. Linear means you have like a linear first order. Means you have something like y prime plus p times y equals some g of t, right? So there's no y on the right side, no y on right side. So this guy here, not linear. Okay, so what is this? It's not homogeneous because if I replace the y with a constant times y in the power of e, I'm not going to get the original back. Note, what we have here is we have a v prime plus a v plus 2e to the minus y v to the minus 1. If you can imagine that there's a 1 in front of this, what if I call that 1 some function? Let's say I call it p of y. So I have a v prime plus a p of y equals, let's call this some other function, like a g of y times v to the minus 1. What form is that? It's Bernoulli. It's the guy we learned today. So we end up in a Bernoulli situation. I don't know if that's, I know if we're in a scenario for this, but I'm going to put it anyway. Yeah. It's somewhat surprising that this guy we just learned about shows up. It's Bernoulli. You're like, oh, we just learned that. Okay, so it's actually a Bernoulli. So by doing this, you end up in a Bernoulli. So that's what we're going to do. We're going to have to do this by Bernoulli. So now what I would do is we're going to have to do another substitution on top of this. So if we have this means here what I can do is set some other variable. Set, I don't know, w equals v to the 1 minus a minus 1, because this here is our n in the Bernoulli. So I'm going to plug in w equals v squared. This means that my w prime is going to be 2v prime, which means that my v prime is going to be w prime divided by 2v. I am going to plug these guys in. So my v prime is w prime divided by 2v plus v equals 2e to the minus y times v squared, v to the minus 1. Now what I can do is I can multiply by 2v everywhere. So this is w prime plus, this would be 2v squared. This would be 4e to the minus y. And my v squared is actually w. So this would mean I get a first order, 1 plus 2w equals 4e to the minus y. This guy is now, this guy's linear. This is first order linear. So I'm going to find the mu, which is e to the integral of 2. This is going to be dy. It's going to be e to the 2, e to the 2y. This side then is going to be e to the 2y, w, all prime. Over here, if I multiply by e to the 2y, I would get 4e to the y. Going to integrate both sides. Going to get e to the 2yw equals 4e to the y plus a constant. This means that my w is equal to 4e to the minus y plus ce to the minus 2y. This means, if I do a back substitution, my w was v squared. And I can therefore take my v to be, well, plus or minus the square root of that. And what was my v? My v was y prime. Back substitute again. Now at this point, you're probably thinking, oh, so this is why Jhevon said he wants to show us another method, because the suggested method, this was actually a problem from the textbook, and this was the method they suggested. But after going through this, I was like, there's got to be a better way. Like, I mean, I can get to the answer, but man, this just feels like too much. Anyway, this here is separable. So this is dy over the radical of 4e to the minus y plus ce to the minus 2y equals plus or minus dt. And I'm going to integrate both sides. Now the integral of the left side is it's very strange. It's a really tough integral. It's very tough, especially if you don't see what to do here. But here's a way to deal with this. I'm going to multiply and divide by e to the y. This brings me into this situation, e to the y dy. Now, e to the y, I'm going to think of as the square root of e to the 2y and bring it inside the radical. So this leaves me with 4e to the y plus c under the radical. And it turns out with this guy, you can actually do a substitution. Say u squared equals 4e to the y plus c. Then your 2u du is going to be 4e to the y dy. Or in other words, 1/2 u du is going to give us the e to the y dy. And so I would plug that in. So I have 1/2 u du. That replaces the e to the y. The radical of 4e to the y plus c, well, that's just u by my substitution. So that's just, this cancels. So it's just 1 du. So the integral of that is 1/2 u plus c. And on this side here is going to be plus or minus t plus a constant. Well, plus a second constant. by the way. Because we already had an arbitrary constant c up here. So this is actually going to be a second one. So we have that. Now I can replace my u with what it was before. This is the square root of 4e to the y plus a constant. Now I can square both sides. And here I would have e to the t plus some constant. And so here I have e to the y. Yeah, I just got it, Roberto. Yeah. E to the y. And so now you just add the c to both sides. You have t plus d squared plus c and that. So I believe this was problem 47 in section 2.9, and that's how they have the solution written. And that's how you got to it. So you start off with this thing, which seems innocent enough, but you get in a situation where it's now Bernoulli. You do the Bernoulli strategy, you now end up with a linear situation, do the linear strategy, and then you back substitute twice, do a crazy integral. Eventually you get to the answer. Okay, so that's the answer. Now, I want to do another way because I did that. This was the method suggested by the book because it taught this method that I mentioned to you guys, and then it says, hey, try these examples. So I actually wanted to do this another way. It is long. So this is just a particular example. Like, of course, I wouldn't put this on a quiz. I wouldn't even put a problem like this on a test unless I give you another hint. So. Yeah, it's a funny story behind this one. Multiple hints. Hint number one. I'll put multiple parts, and each part has to have a hint going to it. Yeah, this is like one problem for the whole exam. Like this tests you on like a whole bunch of things from first order in one problem. But there's another way. So I did this. Funny story how this actually came about. I looked at this method, I tried a few examples, and it didn't seem like a big deal, right? So I tried this example, and it wasn't a big deal. I'm like, ah, that's separable, so it's not bad. So I picked this example randomly from the book, just randomly picked it and threw it and said, hey, let's do this example of the class. And then during the class, it ended up in this crazy thing. I'm like, damn. All right, so at this point, I'm like, man, that's just crazy. So that's what you get for picking examples that you don't work out ahead of time. Sometimes it works out, sometimes it doesn't. So we ended up in this situation where it's just crazy. And I'm like, there had to be a better way. So I went and I spoke to one of my friends in the math department. He works a lot in PD. So he works with ODEs and PDs all the time. That's his specialty, right? So he just noticed something that you would notice that if you did PDEs, or because you're going to end up in a situation where you're looking at differential operators all the time. So he noticed something like he noticed that, you know what, this side here reminds me of the second derivative of an exponential, and I'm going to actually explain what that is. So this is when you're going to look at and use a pattern to help you. So here's another way to do this problem. Here's how here's what he saw. Like, even I didn't see this at first because I was mentally locked into the hints that the book gave us. The book gave us this strategy, and I was like, okay. So Notice, look at what happens here. What if you wanted to take the second derivative? Yeah, we're going to look at an exponential equation. What if you wanted to take the second derivative of something that looked like e to the y? Well, by the chain rule, that means you're taking the derivative of e to the y. The chain rule tells you to differentiate e to the y, you're just going to take the derivative of the power times the original function. And then to differentiate that, you're going to use the product rule. So you're going to differentiate the y prime, which gives you a y double prime, leave the e to the y, plus you leave the y prime, differentiate the e to the y. So that gives you y prime that. So here I did product rule. Notice what this is. This actually is a y double prime e to the y plus a y prime squared e to the y, which is y double prime plus y prime squared times e to the y. Which, if you're working with this sort of thing all the time, that's a pattern you're going to notice. And if you look at this guy, and you look at this guy, the y double prime plus, you notice that, hey, that's actually the same guy. So you can actually do that. And now look at how it can, look at how things can be easier when you notice certain patterns. This leads to the following solution. First, multiply both sides by e to the y. Notice that the second, the left side is actually e to the y double prime, which means you can integrate this and you would get e to the y prime by the fundamental theorem of calculus. This side you're going to get like 2t plus a constant. And then you integrate again. And by the fundamental theorem of calculus, this gives you e to the y. This side you get t squared plus a constant times t plus some other constant. And that's your answer. That's just a quadratic, which the original equation, if you multiply this out, this is a quadratic. And so that's the solution. 3 lines. Just by noticing this pattern. So yeah, noticing patterns, very powerful. Realize that you can, a simple, maybe. I leave it like this, you could. This is allowed. Or you can just say y is going to be ln of this. I left the solution in this form because in the book, that's the form that they left the solution in. But yes, you could just ln both sides to get the y. For some reason, the back of the textbook left the answer in this form. So that's why I wrote it in that form. But yeah, we can take advantage of that pattern and get that guy. And that's this, the miscellaneous ODEs. Now, I did want to talk about at least this, but I guess we'll save that for another class. Oh no, never mind. We do have time. I thought that my other class ends at like 20 to the hour. Oh, we have more time. Awesome. But yeah, so these are just some other methods that you should know about how to solve. You're kind of forcing first and second order ODEs into patterns that you have miscellaneous or mysterious. They could be mysterious. Oh, here, let's fill in the date here. Yeah, so these are just some miscellaneous techniques. So 2.9 goes into some of those, and these are just some of the ones that we are in our syllabus. Bernoulli, very important type, which we had before. Riccati is another famous one. It's also discussed in this section, but for some reason, traditionally, we just don't do it in 391 for whatever reason. So we're going to skip that. Now, the next thing we're going to move into is second order ODEs, which I have the notes for here. But before that, we actually need to talk about some preliminaries. Now, these guys are some things. The first section here, I'm talking about EUTs. The EUT is just short for the existence and uniqueness theorems. Okay. Now, I'm just going to mention them, but we are going to talk about that later on. So when I come back to discuss the important ideas from 2.8, as well as 4.1, and why things work out the way they work out, I'm going to come back and I'm going to talk about the EUTs and how they actually apply to what we're doing. However, moving forward for a while, we're going to be doing things that to some student might seem strange. So I just want to meet it head on and just say, it's okay that we can do this. I will explain later. Okay, so we are going to be doing things like assuming an nth order linear ODE has n distinct linearly independent solutions, and the general solution is a linear combination of these solutions. So I'm going to talk about things like that. You're going to see me addressing things like that pretty soon. I'll also be doing things like, we're going to make random guesses as to what a solution looks like. We're going to work out a method that actually conforms to the way that we assume the solution looks like. And then we're going to be like, okay, all possible solutions are going to look like this thing that I randomly guessed just now. And that's going to be strange for some people. I know it was strange for me. So back when I was a tutor, oftentimes I used to public tutor, like when I used to tutor in the math department at City College or tutor in the science division. A lot of times I would actually tutor classes ahead of the class that I was in, because for some reason students don't get this, but it's actually true. If you understand the basics and your prerequisites, it's easy to get newer things. So there were times back when I was only a Calc 3 student, I was tutoring students in differential equations and all these other things because they just pretty much told me, here's a strategy that my professor gave me, and I used my Calc 3 knowledge to solve it, right? So there was one time this student came in with a differential equations problem. I'm like, I didn't take differential equations, but I'll help you out if you want. And he's like, oh, well, the professor said, guess that the solution looks like this, and then it's going to work out. And I'm like, what? That doesn't make any sense. Like my Calc 3 brain didn't make any sense of that, because you never really do anything like that in Calc 3. What do you mean guess? So it's like, pretend the solution looks like this and then it's going to work out. I'm like, okay. So I did it. It worked out. But it didn't sit well with me that I could just randomly guess this thing and that's the answer, really? So we're going to be doing things like that. And some of you might see, that's really weird that this works out. That's very strange, very convenient, isn't it? And I just want to nip it in the bud and say, you know what, this is okay. And it is okay because there are these important theorems that we're going to skip over for the moment that are going to allow us to come up with these strategies that we're going to be using soon, right? So there are two theorems that deal with first order equations. This deals with first order linear, this deals with first order nonlinear. Then there's one theorem that deals with the nth order linear situation. Basically, these guys say a very important fact. These are called the existence and uniqueness theorems. So the first one is the existence and uniqueness theorem for first order linear equations. This is the existence and uniqueness theorem for first order nonlinear equations, like general equations. And this is the existence and uniqueness theorem for nth order linear differential equations. Basically, here's what they're saying. Under certain conditions, namely conditions that have to deal with continuity, if I have a differential equation of this form, and I have an initial condition that's given to me of arbitrary forms, t0 and y0 can be anything that makes these guys continuous on some open interval, then I am guaranteed to be able to find a solution to this differential equation that actually fits the initial condition that is given, and that solution is going to be unique, meaning there's only one, right? So this is a theorem that says a solution exists and it's unique. Under these conditions, there is a solution and there's only one. So basically, This puts me in a situation where if I have a first order solution, I guess what form the solution is in, and actually find a way to get the answer in that form, then that's the only answer that's around. I can consider that as the solution to the differential equation. There's no need to look at any other thing. So this was like in the case where in lecture 1, where we looked at the equation y prime equals y. And we saw that y equals ce to the x was a solution to this. And then I said, that's the general solution. How did we know that was the general solution? How did we know that there wasn't some other function that we're not thinking about that could also solve that ODE? It turns out we know that because of this theorem right here, the existence and uniqueness theorem. Once you find an answer and it has the arbitrary constant in place, then it is the only answer. All other answers must conform to that answer. So every possible solution that could exist to the differential equation y prime equals y with some given initial condition, I will be able to write any such solution as an exponential, anyone. And there is no need to look for another solution. So we guess that the solution ce to the x would, y equals ce to the x would work. And it turns out that our guess covers all possible scenarios. And we can have comfort in that because of the existence and uniqueness theorem. Similarly, for the nonlinear case, this also works out. However, we need that the partial derivative with respect to y is continuous on the region that the initial condition is given. Then I can say the same is true for the nonlinear first order. For the linear first order, this is actually pretty straightforward. The integrating factor method is the proof for that. For the nonlinear case, the proof is a little bit more involved, let's say the least. It turns out for the nth order case, this also, a similar situation holds. If I have an nth order linear differential equation, y to the nth derivative, blah, 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 going down to g of t, and I'm given a set of initial conditions that are, for all intents and purposes, arbitrary, then if these coefficient functions are continuous on the interval where the initial conditions are given, on some open interval where they are, then there is a unique solution to this differential equation that will fit those initial conditions. So the solution exists and it is unique. And moreover, we know what form it's going to be in. The solution will look like this. It is going to look like c1y1 plus c2y2 dot 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 c up to cn yn plus some particular solution, where the c's are all constants, the y's are functions that are what we call linearly independent, and I'll talk about those later on, but it means that they can be thought of as distinct somehow. And the yp is just a solution that plays well with this g of t over here. So it turns out, if I have an nth order linear differential equation, under the conditions that the coefficient functions are continuous on an interval, then I can find a unique solution on that interval that fits any set of initial conditions I'm given on that interval. The existence of a solution is guaranteed. Moreover, the solution is unique, and I can write it in a very specific, predictable form. This means that if I were to guess what a solution might look like, and I would be able to actually write that down as a solution, and I can fit the initial conditions, then it turns out that any possible solution that could exist in the universe will conform to my guess. I have the power to guess and still be comprehensive. That is amazing, and it's actually something that we have by the existence and uniqueness theorem. And so a lot of things that we're going to be talking about are going to conform to what we want them to conform to based on this situation, which is crazy, but it's actually true. And that's actually something we'll talk about in a bit. But before that, something that we're going to need even more soon based on things, second order ODEs that I'm going to cover with you guys tomorrow, I do need to talk a little bit about complex numbers with you guys. I'm not going to be comprehensive. I just want to tell you enough about complex numbers that we are going to be able to use in the future for this class, so you're not completely lost, because we don't really cover complex numbers in this class at City College before this class. But then you get to this class and they suddenly expect you to know about complex numbers. So yeah, I'm going to tell you about complex numbers. All right, so let's jump in. The set of complex numbers is a set of numbers that looks like that. A plus IB, where A and B are real numbers. So for example, 1 plus 2I, or 3I, or radical 2 minus 5I are complex numbers. So they have this part here, the real number that's standing by itself, that's called the real part. And this part here, the guy that's attached to the I, is called the imaginary part. It's called the imaginary part because the number I is called the imaginary unit. The imaginary unit is defined by I equals the square root of -1. So forever, you've been told that you can't take the square root of a negative number. It turns out there came a point where for the math to work out, we had to pretend that this guy had a solution. So we call that solution I. I is the square root of a negative number, right? So it came about when we were considering an equation like x squared. Yeah, you laugh, but it's actually true. We were like, we'd like to have a solution for this equation. Let's just make one up, call it I. Can you really believe we imagined such a solution? Yeah, let's call it an imaginary number, right? So that's the birth of complex numbers. Now, granted, complex numbers are highly applicable. They are so useful, and we're going to see a lot of uses for them in this class, and in your future classes and in future applications, you're going to see a lot of uses. We pretty much said, let's pretend there's a solution to x squared plus 1 equals 0. Well, that would mean that x squared equals -1. There is no such real number. Okay, let's make up an imaginary number where that's true. Call the number I. So I is going to be a number such that I squared is -1, which means that I is the square root of -1. That leads to a whole set of numbers that are called complex numbers. And the complex numbers are very useful because now they allow us to solve nth degree polynomials. Any nth degree polynomial now will have n solutions up to multiplicity, and that's actually pretty useful. So now we can solve equations that we couldn't have solved before, like x squared plus 4 equals 0. So I could solve that by just saying, okay, x squared equals -4. Then I would be able to take the square root of both sides. And you're like, well, square root of 4 doesn't exist. Well, now it does. Basically, you think of this as 4 times -1. You would split this into radical 4 times radical -1. Radical 4 is, of course, 2, and then radical -1 is I. So the solution to this is x equals plus or minus 2I. So now we have a way to solve this equation, which when you were back in algebra and pre-calc at City College, they told you there was no answer, no solution. Yeah, there is a solution. We now know that it's in the complex numbers form. Another situation is, look at this quadratic. We can solve this by, okay, good. So some people would have seen it in high school, but I know for a fact that City College ignores complex numbers in the entire calculus sequence. So I just want to make sure that we're all kind of up to speed. So yeah, some of you might have seen this before, but at City College, we don't do complex numbers. So here you have a quadratic equation. This one is hard because you can't really factor it, but you can use the quadratic formula. So here you can do it by the quadratic formula. Your x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Then you plug that in. So your b was -4, so minus b is 4 plus or minus the square root of b squared. That's 16 minus 4 times a times c, that's 7, all over 2 times a. So you're going to notice that this is going to be 4 plus or minus the radical. Now that is 16 minus 4 times 7. So that's 16 minus 28, right? So that's going to be what? It's minus 12. Now before, the radical of minus 12 was something we're like, okay, I guess we all have to go home now, can't do anything. But now with the power of complex numbers, this actually has a solution. Here we would think of this as 4 plus or minus the radical of 12 times I. Now, of course, radical 12, you can write this as radical 4 times 3. So this is just 2 radical 3. And so this is 4 plus or minus 2 rad 3I all over 2. And so you get 2 plus or minus radical 3I. And so that is your answer for x. Okay? So with the complex numbers, we're now able to solve things that we couldn't solve before. And it's not just a party trick. It's actually very important that we are able to do this. So yeah, those are some examples. Also, you can notice some other things here. If your I is the square root of minus 1, yeah, we solved the impossible. If your I is the square root of minus 1, then if you square both sides, you would get minus 1. I squared is minus 1. If you cube that, or you can think of that as multiplying by I, you get minus I. So I cubed is minus I. Your I to the 4th is if you multiply by I again, you get positive 1. Your I to the 5th gives you I, and you start over the process. So you can start with I equals the square root of minus 1, keep multiplying by I, and you'll go through a pattern. It will go from I to minus 1 to minus I to positive 1, back to I to minus 1 to minus I to positive 1. Once you keep raising I to another power, you will go through this cycle. The cycle is length 4 long, and it repeats. This actually helps us to establish an important fact, which is the next preliminary I'm going to tell you about. It's called Euler's identity and Euler's equation. This is something that helps us deal with the expression like e to the ix. Now, of course, the above is a surprisingly useful number, and here's how we can figure out what that guy is. So we all remember, of course, that e to the x as a series. We learned that in Calc 2. If you did Calc 3 a few years ago, you would have learned it in Calc 3. But we learned in Calc 2 that we can write this as a Maclaurin series. N goes from 0 to infinity of x to the n over n factorial. And I know that we all remember that because this is something that you should all remember. Okay, so this means that if I look at e to the ix, this is the same as the summation of ix to the n over n factorial. So now what we can do is we can start to write this out. So this is going to be 1 plus ix over 1 factorial plus I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial plus I to the 4th x to the 4th over 4 factorial plus I to the 5th x to the 5th over 5 factorial plus dot dot dot. Now, we can rewrite these i's in terms of guys that this list I have up here. So this here, 1 plus ix. Notice that the I squared I can think of as minus 1. The I cubed I can think so here I applied the above. Right, so here I'm applying the guys that I mentioned up here. Now notice what we can do. We can group all the guys with i's in them and group all the guys without i's. So the guys without i's, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. The next guy would have been minus x to the 6th over 6 factorial, dot, dot, dot. If you put the guys with i's in them, you would have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. The next guy would actually be minus x to the 7th over 7 factorial, dot, 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 dot. And again, of course, we all remember that guy is just the actual Maclaurin series for the cosine function. And this guy is actually the Maclaurin series for the sine function. And so we get an important equation called e to the ix is actually cosine of x plus I times the sine of x. Usually we use theta because of the angles. E to the I theta is cosine theta plus I sine theta. This, ladies and gentlemen, is called Euler's equation. And that's what this all leads to. So Euler's equation, that's it. This is something that we need to have memorized. So from now on, this is just something that we know. This is why I'm putting it in a box. Now, there's a very nice thing that you can have, which I'll just stop by here. Notice if we plug in theta equals pi, we obtain the following. We obtain e to the I pi is equal to cosine of pi plus I times sine of pi. Sine of pi, of course, you remember is 0. Cosine of pi, you remember is minus 1. So you end up with e to the I pi equals minus 1. What you can do is you can move this over. E to the I pi plus 1 equals 0. And that leads to something that's called Euler's identity. E to the I pi plus 1 equals 0. This is considered by a lot of people to be the most beautiful equation in all of mathematics, right? So this is called Euler's identity. It's beautiful because it involves some of the most important mathematical constants around. E, I, pi, and 1, and 0, right? 0 is the additive identity for the real numbers. 1 is the multiplicative identity for the real numbers. E to the x is the most important function in all of mathematics. E is obviously an important number. Pi is important. We get these when we are thinking about circles and a lot of geometry. Pi comes into play. I is the guy that allows us to solve any polynomial there is and find n solutions up to multiplicity for an nth order polynomial. Plus is the important one operation of the real numbers. It's the addition operation. If we think of the real numbers as a field, that's one of the important operations. Multiplication is an important operation if we think of it as a field, which we have multiplication with the I times pi, and exponentiation is another important operation. So here in this one very short equation, we have all the important mathematical constants. We have all the important mathematical operations in one nice equation. And we have a situation where we have an imaginary number giving us 0 when added to a real number. And that is beautiful. So a lot of people, they'll tell you about, I remember the day I met my wife, it was 1969 and she was wearing a red dress. Like mathematicians remember the first time they saw this equation, right? They worked this out and like, wow, that is beautiful. And I'm telling you guys for no other reason than that. So this is the guy that you guys really need to know. But this is a guy that you should know it. You should know. So that's called Euler's identity. All right. Now, for us, this guy, Euler's equation, is very important because it allows us to make certain computations. For example, like here, e to the I pi is minus 1, shown previously. But we are going to need to know how to work out similar guys to this in the very near future. Guys like these. Right? So you have e to the I pi over 2. What is that? Well, this is cosine pi over 2 plus I sine pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So e to the I pi over 2 is going to be I. That's going to be important for later. This is something that you should just kind of know automatically, even though technically you could work it out. E to the I 3 pi over 2 is the same kind of idea. What is that expression? We can compute this by thinking of it using Euler's equation. Cosine of 3 pi over 2 is again 0. Cosine of any odd multiple of pi over 2 is going to be 0. Sine of 3 pi over 2 is minus 1. So this is a way for us to generate minus I. Think of e to the 3 pi over 2. That generates minus I. Then we're going to want to know how to think of it when we take an exponential and put a complex number in the power. Well, you would think of it as e to the a times e to the ib, and apply Euler's identity on the second scenario. So this is going to be cosine b plus I sine b. So this is e to the a cosine b plus I e to the a sine b. Okay, that's going to be important. Like literally, as of the beginning of next class, it's going to be very important for us to know this guy. You can look at something like e to the ibt. So here t is just some variable. Or think of this as some independent variable. So if I put e raised to a number times t, where the number is a complex number, what I would think of this is as, well, this is e to the at times e to the ibt. And I think of that as being just another number on its own. I would be able to write this as e to the at, apply Euler's equation. This will give me cosine bt plus I sine bt. Therefore, I'll be able to expand this into e to the at cosine bt plus I e to the at sine bt. Now, that is going to be relevant as of tomorrow's class pretty much immediately, right? So we can get these preliminaries by learning a little bit about complex numbers and about Euler's equation. Very important stuff for you to know. We will talk about the existence and uniqueness theorem again at a later point, but like I said, if I spend the class or an entire class talking about that, which I probably am going to end up spending an entire class, it's going to be too much of a rush for the exam next week. So we are going to stop there for now. So now we know about some miscellaneous situations or mysterious situations to solve using first order ODE techniques, as well as some preliminaries about complex numbers and Euler's equation. If I recall correctly, your exam is on Thursday next week, but it's in the syllabus. I know it's coming up soon. Anyway, we will stop there. As always, I will post the video with the PDF attached to it, and you guys can review everything. But that's it for now. I am going to let you guys go. So thanks for stopping by. Hope you're all doing well. Stay safe, and I will see you guys in the next one. Ciao.